Exercise 8 of Chapter 8 follows up from one of the applications that I introduced in Chapter 7. That was where we used a matrix to house a geometric transformation, and we applied that transformation to a set of points in order to move the points around in space. And I explained that that is the computational basis of computer graphics and video games and so on. Here in this chapter, we are going to continue working with this concept by exploring the impact of the matrix inverse on a geometric transformation. So the goal of this exercise is to write code that reproduces figure 8.6. I will show you that figure in a moment. And I recommend starting by copying the code from exercise of chapter 7, exercise 3. Okay, and then we want to make the transformation matrix non-invertible by setting the lower left element to 1, and then basically exploring what that means geometrically. Okay, so let me start by going up to figure 8.6. That's what you see here. So we have a set of points defined by these black circles here. It just makes a circle on this plane. And then I applied a transformation matrix to the XY coordinates of those points to transform this circle into an ellipse that you see here, these gray squares. And then I used the inverse of the transformation matrix to get from the transformed data point, so from this ellipse back to the original data points, which is indicated by the X, so the inverse transformed. Now, this is a little bit trivial when, the fact that applying the inverse transformation to the transformed points gets us back to the original point. That is a little bit trivial when you look at the algebra, when you look at the equations. So here we have the new points defined as Q, and that is the original data points times T, the transformation matrix. And here I show that when we apply T inverse, so the inverse of the transformation matrix, then the resulting U is going to equal P. Now, when you look here, this is pretty trivial because T inverse times T is the identity matrix. So we're just saying U equals P. Nonetheless, I included this discussion here because I believe that this image, thinking about the geometry of the inverse, when we conceptualize a matrix as a transformation, a means of transforming a data set, and the inverse is the undoes that transformation, I think that's conceptually very insightful. Okay, so now I will switch to Python and show you my code, which I copied from the previous chapter and then modified for this figure. Here we have the transformation matrix. I have 1 and 0.5 in the first row and 0 and 0.5 in the second row. Here I'm computing the inverse of the transformation matrix. I call that variable ti. So then I define these points here. These are angles, and then just say cosine and sine of those angles. That creates a matrix of data points, or coordinates in this case. And this code should look familiar from the code in the previous exercise. Okay, so here I take those data points, those coordinates, and apply the transformation matrix. And here I apply the inverse of the transformation matrix and get the back transformed results. And then here I'm just doing a bunch of plotting. Okay, so not super amazing. That just reproduces the figure that I showed in the book. Now, the next step of this exercise was to make this transformation matrix be non-invertible by changing the lower left element to 1. So now you can see that the first row is the same as the second row. You could also say that the first column is a scaled version of the second column. Either way, it is no longer invertible. Now, we can try running this. We're going to get an error message over here. We don't even get the plot. Because this is a singular matrix, it is not invertible. What I'm going to do for starters is just comment out that line, comment out this line, and let me see, comment out this line, just to show you what the transformation looks like. So here we have the original data points again, and here is the transformed data points coming from the singular transformation matrix, the non-invertible transformation matrix. And I hope that this also gives you some geometric insight into why a singular matrix, a transformation matrix, cannot be undone. It cannot be inverted. And you see the geometric intuition for that here. So all of the new points lie on a line. This is a line. These are points on a one-dimensional subspace. And now that means that it is impossible to get back from this one-dimensional subspace to the original image. For example, these data points here, is this supposed to go over here or is it supposed to go over here? There's no way of knowing based on this transformation because it is singular. Okay, so let me undo these. Now, so the question in the book was, how do we fix this? How do we address this? Now, you could think of using the pseudo inverse. That's going to fix the problem in the sense that now, Python is going to run the code without producing any error messages. But that doesn't really fix the problem because you can see that the inverse transform results are still not getting back to where they originally were. Now, we could argue whether this is better, whether it's kind of close, the pseudo inverse. It is now within the range of the circle. So, we've undone the smearing, the spreading outside of the range of the circle. So now all of the back transform points are inside the radius of the circle. But I mean, that is not a very satisfactory back transformation. The point is that when you start with a singular matrix, there is nothing you can do to get back to the original data points.